Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 5. Open Methods, Secant and Modified Secant Methods. The secant method is a numerical technique used to find the roots, or zeros, of a real-valued function. A major handicap of the Newton-Raphson or modified Newton-Raphson method is that both methods require derivatives of the nonlinear function f(x). Finding explicit expressions for the derivatives of some functions can be difficult or may result in complicated expressions. The secant method that is similar to the Newton-Raphson method but does not require the computation of the derivative of the function. Instead, it approximates the first derivative using two prior estimates of the function and iterates through successive approximations until the root is found to a desired level of accuracy. The method, just like Newton-Raphson, is based on finding the tangent lines, followed by calculating the intercepts that eventually approach the true root. Let the two required initial guesses be x0 and x1. The corresponding ordinates are found and labeled as shown. After finding the ordinates, we obtain p0 and p1 points on the curve. The line passing through p0 and p1 is the secant line, while the extended tangent line to the curve at p1 cuts the x-axis at x2, which is an estimate closer to the true root. The slope of the secant line is obtained from the right triangle. The slope of the tangent line to the curve, i.e., its derivative, at point P1 is set to the slope of the secant line. To find x2, we use the Newton-Raphson iteration equation, where the derivative is replaced by the above approximation. Next, we find the vertical projection point P2 on the curve. Using P1 and P2, we are able to calculate the slope of the secant line. By replacing the slope of the tangent line T2 to the curve with that of the slope of the secant line, we find the following approximation. Using this approximation in the following Newton-Raphson iteration equation, we obtain. To generalize the iteration equation, we replace f'(x) with the following approximation. Here, we assume that the magnitude of fxp is the smallest of the last two estimates. After simplifications, the iteration equation for the secant method becomes, or we may rearrange it as follows. However, as the iterations progress, xp and fxp must also be saved for the next iteration besides xp minus 1 and fxp minus 1. In this algorithm, we propose to swap the two estimates and the corresponding ordinates if the magnitude of fxp is greater than fxp minus 1. Consider the following nonlinear equation. Find its root for the given initial guesses and stopping criterion. Two initial guess values are given as 3 and 2. We then calculate the ordinates as follows. We note that the magnitude of fx0 is greater than that of fx1. Hence, no swapping is necessary. So we record down these values. Then, we calculate delta, which is the ratio of fxp to f'xp. The absolute value of this quantity is also the absolute error between the last two estimates. Using the delta and x1 values, we can estimate x2 as 1.874762 as follows, and we note this down. The last two initial guess values are 2 and 1.8747,619. Since we had fx1 in the prior step, all we need to do is to calculate fx2, which we find it to be 17.584814. Notice that the magnitude of fx1 is greater than that of fx2. Similarly, no swapping is necessary in this step either. Next, we calculate delta to be 0.2526,955. Using x2 along with this value, we estimate x3 as follows, which yields 1.622,664. Repeating this procedure successively yields a sequence of estimates x4, x5, and so on. The iteration procedure in this example yields the converged solution after 8 iterations. The true root is an estimate obtained to 9 decimal places of accuracy. The 9th estimate is obtained as 1.38435398, which has an absolute error of 7 times 10 to the minus 9. The advantages of the secant method are: the secant method is simple and easy to apply. It requires only one function evaluation as opposed to 2 evaluations in the Newton-Raphson method. It does not require derivatives. Starting with a set of initial guesses in close proximity to the root, the method converges very rapidly, faster than that of bisection and method of false position, with an order of convergence of 1.62, that is, superlinear convergence. The disadvantages of the secant method are: it requires 2 starting initial guesses. It suffers from many of the disadvantages of the Newton-Raphson method. Its convergence behavior depends on the function and the proximity of the initial guesses to the true value. The current estimates have no assured error boundaries. It may not always converge to a solution for the same reasons also pointed out for the Newton-Raphson method. The modified secant method is modified in the sense that it requires only one initial guess, and f'xp is replaced by the following approximation, where h should be chosen small. Then the iteration equation for the modified secant method leads to the following equation. This equation uses only one initial guess and does not require the derivative of the nonlinear function. The prior example was also solved by the modified secant method by taking h equals 0.1. The results are presented in the following table. The value of h is relatively large. Yet, the solution converged after 8 iterations with the same stopping condition. The same example was solved with h equals 0.001, i.e., 100 times smaller. For this fairly small value, the results are presented in the following table. The iteration process, in this case, yields the approximate value after 6 iterations using the same stopping criterion. That is all for now. See you next time with another topic. Bye.